All right, I want to go ahead and show you problem number 3 on the 2015 exam. You figured out by now I gave you one problem off the 2014 exam. I just felt strong about that, and I skipped problem number 2 in the 2015 exam. I hope that wasn't okay to do. Well, I guess you'll know after Thursday. All right, problem 1, they gave you the structures. Obviously, I'm not going to write those again. That'd be kind of hard to do anyhow. Which compound, lauric acid or sucrose, is more soluble in water? And justify your answer in terms of intermolecular forces present. Okay, you get a point. I'm talking about hydrogen bonding, and you get a point for talking about comparison of force. Basically, I said sucrose is more soluble due to the higher number of OH molecules exposed, leads to hydrogen bonding with the water molecules. And then lauric acid does have a polar end, but a very long non-polar end. Thus, it does less interaction with the water molecules. And so that's my answer. That's my justification. And looking at their answer, that would be correct. Okay, for it be acceptable enough. For part B, it says, assume you have 1.5 gram sample and all of it goes into the water. How much of a temperature increase you're going to have? So basically you get Q equals MC delta T. And you have 1.5 grams of the lauric acid. I'm just going to put LA. And you're told that it is 37 kilojoules per gram. And of course, 1 kilojoule is 1,000 joules. The mass of water is 325 grams. And the heat constant of water is 4.184 joules per gram degree Celsius times delta T. And then I solved for delta T, and I got 40.8 degrees Celsius. Since it gave us initial temperature is 25, then I said this is 41 degrees Celsius. And so TF equals 25 degrees plus 41 degrees equals 66 degrees Celsius. So the final temperature would be 66 degrees Celsius on that. Okay, an attempt to determine the heat of combustion of lauric acid experiment. A student placed 1.5 grams in a ceramic dish underneath a can made of aluminum containing the water, etc. Aluminum ignites the sample with a match and records the highest temperature reached by the water. The experiment is repeated. The can of the same mass. This time the can is made of copper. Specific heat of copper is 0.39. Specific aluminum is 0.9. Will the final temperature of the water of the can made of copper greater than, less than, or equal to the final temperature of the water by the aluminum? Okay, the copper can, the water temperature will be higher. And why is that? Well, copper has a lower heat capacity than aluminum. So the copper will absorb less heat. In other words, it's going to heat up faster. So that means there's going to be less energy going into the copper than going to the aluminum. So therefore, there'll be more heat energy going into the water, therefore making it higher. So again, 1 point for the correct answer, 1 point for explaining it. Letter point 2 says, in both experiments observed the final temperature of the water was less than the final temperature calculated. Identify one source of experimental error that might account for this discrepancy and explain why the error would make the measured final volume lower than predicted. And I said, well, some of the heat of lauric acid is going to be lost to the environment, the ceramic dish and the air. And since heat is lost, the heat energy to the water will be less, therefore making a smaller TF. And so again, I think that would both those answers would be what they're after there. Part D says the experiment described above is repeating using a 1.5 gram sample of sucrose. The combustion reaction for sucrose in air is represented by, they gave you this reaction, and said even though delta G for the combustion of sucrose has a value of negative 5837, the combustion reaction does not take place unless it is ignited. Okay, it's a huge heat of reaction, we know. But what about reaction? Why you have to ignite it first? And I said you got to get activation energy. They love that term. So let's put the higher activation energy, have the high activation energy. Once ignited, the energy from a few burning molecules will provide enough energy for the reaction to proceed. But you've got to get past that activation energy. And then D, predict the sign of delta S for the reaction and justify your prediction. I said the delta S is positive since it's measuring the entropy. The disorder increases. If you look at that reaction, you get 23 moles of gas being produced for every 12 moles of gas being being used. So therefore, we have much more gas on the product side, making it much more disordered. So therefore, delta S being favored and giving it the positive value. All right, so I'm going to stop on that particular problem.